Hi, this is the final video for the cosmological perturbation series. The 8th video for the what is the observational things in this the cosmological perturbation. So in the previous video, in the 7th video, we know that the primordial perturbations arises from the impulations and they can be described by the curvature perturbation curly R. And this primordial perturbations will be transferred to the matter path spectrum via the evolution. On the superhorizon scale, these curvature perturbations are just a constant, but some specific modes that enter the horizon, and each mode that evolves depending on the universe's radiation dominance or the matter dominance era. And these evolutions are encoded in the transfer functions capital T. So the primordial perturbations now will be transferred to the density perturbations via the transfer functions, which includes the evolutions information. During the RD, the process has important role, so the perturbations not grow significantly. They have just a logarithm growth behavior, but also the coupled photons variable is the makes the acoustic oscillation. But during the matrix dominance era, the process is negligible. The equation of the size is 0, so the matter perturbations grows linearly about the scale factor. And from the distance perturbation delta, we can extract the statistical property by the two-point correlation functions, and we can define the power spectrum P of the K. So this power spectrum P of the K can be related with the primordial curvature spectrum P of the K R with the scalar of the transfer function. And this primordial spectrum has a nearly scale invariance. So about the K, the spectral index is almost the 1. So the shape of the PK series, the power spectrum series, primarily determined by the transfer function. For the large scale mode, they enter the horizon later, so the primordial spectrums still remain, but the small scale modes are suppressed by the entering the horizons during the radiation dominant era. So these matter path spectrums can provide the theoretical predictions of the large scale structures, like as a galaxy and the cluster, and they can be directly compared with the observational data. So what are some specific parameters that we can prove the distance perturbations and the matter path spectrum? Usually we can define the spectral index for the scalar spectrum or the tensor part, or also the slower parameters from the impulsion model, because the impulsions model will determine the primordial perturbations mode. So first of all, we will introduce the dimensionless power spectrums, capital delta scale, and for convenience. This makes the dimensionless by the k cube. This quantity measures the contribution to the variance per logarithm interval in the k. And one can define the spectral index ns as the logarithm derivatives of this dimensionless power spectrum with respect to the k. So this delta dimensionless power spectrums are parameterized by the power laws about the k with the pivot scale k star. There will be the amplitude as and the spectral index ns. This as and ns will be important parameters which represent the primordial power spectrum this part. Okay. So recall that the curvature perturbations problems, the impulations arising from the following form: Hubble scale and pi dot, where the pi is in Platon's sphere, and the horizon crossing conditions are given by the K for specific mode equal to the AHs, the hover horizon side. So by inserting this relation, then this relation to the here. So we know that the delta R from this relation, and by inserting this relations K equals to the AH is the hover closing condition, then one can express the spectral index NS as the combinations of the H's and the Hubble H's and implanted field pi. And we know that the slower parameters of the impulations models, epsilon the atas are defined like that. So there is a relation between the spectral index and the slower parameter. This is the quite important relations, which gives the primordial perturbations arising from the impulsion. The deviation can arise from the scale non-invariance. Also, similarly, one can define the tensor perturbation part, delta t, and also the tensor spectral index delta t, or the parameterization for this dimensionless tensor path spectrum. And usually one can define the tensor to scalarity R as the ratio between the scalar spectrum's amplitude AS and the tensor part AT. And again, by using the slower impulations relation, this R can be rewritten by in terms of the epsilon. So the R equal to the roughly the 16 epsilon. So if the non-zeros are already detected, this can be the evidence of the impulations and the informations about the slower parameters epsilon. And similarly, the NT, the tensor spectral index, can be related with the slower parameter. So if the impulations satisfied by the slower conditions, then there's a single field, and there is a relation between the tensor to scalarity R and the tensor spectral index NT. These relations are characteristic predictions of the simplest impulations model as a minimal scenario. And also the impulsion analysis scale can be expressed with the Hubble parameters H's, and the related with the tensor scalarity and the path spectrums of the primordial perturbations, and the observation values of this AS is roughly 10 to the minus 9, related with the temperature and isotropies of the CM 10 to the minus 4. So the Hubble parameters can be expressed in terms of the functions of the tensor scalarity of R. So by using that, the impulations model can be tested because the epsilon and atas impulsion slower parameters determine the NS and R for the scalar tensor scalarity and the spectral index for the primordial perturbation. And this NS and R can be constrained by the CMB temperature and isotropy spectrum. Because there are beams of the polarizations of the CMB only arises from the tensor perturbation, so this can prove the R. So the observational results, the NS is nearly the 1, almost invariance around the scale, and R is smaller than the 0.03, nearly the 0. So there is a slight deviation from the exact scale invariance, and this can provide slower impulations with a small epsilon and eta. Also, the upper bound on the R implies the small slower parameters with the epsilon, making the blood impulsion or potentials for the minimal scenario. So there are some several models of the NS and R, and there are some constraints here, and some models are excluded and some models are still able to report this observational data. So the impulations model can be tested by this observational results of the primordial perturbation. So far we talk about the premodel perturbations using the two-point correlation functions, but one can generalize to the higher point correlation functions. There might be the deviation from the Gaussianity, and they are encoded in the higher order correlation function. The leading contributions are coming from the 3-point functions, and similarly, the one can define the bispectrums instead of the power spectrums of the two-point correlation function. Common parameterizations of the non-Gaussianity is written by the following form. Here the first terms that are coming from the Gaussian field, and the second term coming from the non-Gaussianity. In the single field, the slow roll impulations as a minimal model, non-Gaussian is typically small, so that detections of the large non-Gaussianity indicates the physics beyond the simple minimal impulationary model, like as a multi-field impulations or the non-tubular interactions or the no-slow roll impulation model. So today in this video, we talk about how the premodel perturbations and impulations can be tested by the observational data. The curvature perturbation can be related with the slow roll parameters, and this dimensionless power spectrums can be parameterized by NS or R about the scalar and tensor path, and they can be related with the slow roll parameter. Similarly for the tensor perturbation, so there are the relation between NS and epsilon and eta, and the tensor scalarity R and the slow roll parameter. Such a premodel perturbations can be tested by the CMB observational data, so that the impulationary model can be tested by the observational probe. So by this video, we now end this long series of the cosmological perturbation. Several we begins with the Newtonian gravity for the cosmological perturbations with the non-relativistic limits and sub-horizon, and now the such a gravitational Jensen instability can be generalized to the GR, the relativistic bosons around the superhorizon, by solving the Einstein field equations with the matrix perturbation and the matrix perturbations, and we also consider the large gauge invariance variable. Because of this evolution is too complicated, so in the third video we assume that the superhorizon limits around the adiabatic conditions for simplifications, and the fourth and the fifth video we talk about the power spectrums of stomatic components, how the power spectrums arise for each mode entering the horizon source, and the evolutions of the radiation density perturbations, and eventually we arrive at the observational quantity like as the cosmological background CMB. In detail, we also talk about the temperature anisotropies and the polarizations of the CMB, which is encoding information of the primordial early universe. And in the seventh video, we talk about how these primordial perturbations arise. The origins comes from the quantum fluctuations in the impulsion. We quantizing the perturbations and imposing the bound-Davis vacuum, and we obtain the nearest scale imbalance spectra, and they can be characterized by the parameters of the spectral index and tensor scalarity R. So, and the final videos today we talk about how the observations data constrains the premodel perturbations and the impulations and model. So overall, this series establishes overall picture how the cosmological perturbations arise in the early universe, and they evolve, and they can be detected in the realistic observable. So such a framework of the cosmological perturbation theory can provide the directly basis between the fundamental physics in the early universe and the precisions of observations of the cosmology. So this is a very long series. I started in this series in the early size of this years, and various trials to understand this cosmological perturbations a few years ago, and now that we are on this here for this cosmological perturbations, a very long series.